There are three power series to memorize. They are Maclaurin, e to the x, sine of x, cosine of x. It's very helpful to memorize these. You can see the pattern here if you have to expand, and then the general form of the e to the x series. Sine of x, same thing, and the general form, cosine of x. And the nice thing about memorizing them is because now I will show you how we can very nicely use them without having to recreate them. All right, so we know that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so forth. So therefore, like I just said, when we memorize this, we were going to get negative 1 to the n, x to the 2n, all over 2n factorial. So therefore, if we want cosine of root x, what we're going to do is everywhere there's an x, we're going to plug the square root of x. And as a result, then the general form of the series for cosine of root x again, I'm plugging in root x in place of x all over 2n factorial. And there it is, right there. I'm just going to double check. Yep. Okay. And I didn't do that example. And now we're moving on to revisiting geometric series. And what we're going to do is we're going to be given a function, and we're going to turn that function into a geometric series. So for a convergent geometric series, we can find the function f such that f of x is equal to, that looks very familiar, the geometric series. So here we go. And on the AP test and on our test, you will only deal with Maclaurin geometric series, meaning we're always going to be centered at 0. So we have a function here, and we're going to turn that function and change it so that we can get it into the form that looks like this, a over 1 minus r. If we can do that, then we know what a is, we know what r is, and we can turn it into a series. Here's the steps. Number 1, ensure the denominator starts with a 1. So how we do that is I'm going to change the order and change it to 4 plus x. Now we have to ensure that the denominator, well, starts with a 1. We're still in step 1. Well, how do I turn the 4 into a 1? I have to divide everything by 4. By doing that, we get 1/2 1 plus x over 4. Now, step 2, we want to make sure that the denominator is 1 minus. Well, how do we change a 1 plus to a 1 minus? And all we want to do, we don't want to multiply by a negative because I don't want to change that 1 to a negative. So how do I change that plus to a negative? I go like this, minus a minus. That's the same thing as 1 plus. We have now turned this into the form that we want, a over 1 minus r. So we know that a is 1/2, and we know that r is negative x over 4. So we now can turn it into our series. So we can basically say that f of x is equal to n equals 0 to infinity a r to the n. And we just created a geometric power series for that function. So that is done. But now it's asking us to find the interval of convergence. So we know that to be convergent on a geometric, the absolute value of r is less than 1. Well, r is negative x over 4. Whenever we're dealing with an absolute value on the left side, the only thing we want to keep in the absolute value is the variable x, or x minus c, or x plus c. Because we already know we're centered at 0. So if it was centered at something other than 0, like 2, then what we would leave in the absolute value would be x minus 2. If we were centered at negative 2, x plus 2. So I know the absolute value of a negative is a positive, and 4 is just 4. So I can take out the 1/4, and that's left inside. Now recall, I can't call 1 my radius of convergence because there's that 1/4 out front. So we have to multiply both sides by 4 so that now all I have left is the absolute value of x is less than 4. Now I know that my radius of convergence, or we call it big R, is equal to 4. And this, the number on the other side of the inequality, is the radius of convergence. As long as over here, the only thing left is your absolute value, and what's inside is, in this case, an x, because we're centered at 0. All right, so now what we can do is we can now find the interval of convergence. Well, I can look at this inequality, and I can rewrite that as x is less than 4, and x is greater than negative 4. So that looks like that, or we can write it like that. Either one is fine. This is called our interval of convergence. And you might be saying, well, don't we have to check the endpoints? The answer is no. And I'm going to write a note here. You do not need, shoot, hold on here. When that happens, get my pen back here. You do not need to check the endpoints for convergence or divergence with a geometric series, because it always diverges at the end points. That's a nice thing. Makes it a lot easier. You don't have to test the endpoints. And you can see the picture here. At both of the endpoints here, it's diverging, and they're not near each other. And so therefore we know that we're not going to include the endpoints in our interval of convergence. All right, and then the other thing I want to mention is we have some AP questions, which I am going to print for you. The other thing I want to talk about, because there was some confusion, and I talked about this briefly, I think, in each of my classes, I want you to understand the difference between a polynomial and a series. So if you think about this, we use polynomials. So notice I have an approximation. I'm going to just do the second derivative. C squared over 2 factorial. So I'm going to say we're going to find a second degree Taylor polynomial to approximate f of x. So we would take 2 derivatives. When we're talking series, so this would be, we'll call this a polynomial of degree 2. When you're finding the series, you're doing the same thing. Let's go do the second derivative. But it's going on and on and on and on and on. So we're calling this a series. So what happens is a polynomial approximates a function. The closer you are to the center and the higher the degree, the closer the approximation, the closer the polynomial approximates the actual value of the function at a certain x value. A series pretty much identically replicates a function because a series is a polynomial of infinite degree. It keeps going on and on and on and on. But I know there was some confusion on yesterday. Questions were asked, and they were saying, well, which formula do you use when? They're using the same exact formula. It's just the polynomial. You're told what degree or how many terms you're going to use, whereas a series, you have to decide how many derivatives do you need to take so you can see a pattern to create your series.